Welcome to this explainer. Today, we're going to pop the hood on a wonderfully simple yet absolutely powerful machine learning algorithm called K-nearest neighbor, or, just KNN for short. We live in a world that is totally driven by data and automated decisions, and honestly, KNN is a foundational piece of that whole puzzle. So let's dive right into this, because what we're going to see is that this algorithm makes really complex decisions based on a very human concept: the company the data keeps.
Just imagine you're handed an image of an unidentified animal. It's got pointy ears, a long tail, some fuzzy fur, and you need a computer to automatically categorize this mystery creature as either a feline or a canine. Well, this is a classic classification problem, right? And it's exactly the kind of puzzle the K-nearest neighbor algorithm is built to solve.
To pull this off, the model doesn't just make a wild guess. Instead, it analyzes the new creature's features against a massive existing database of known identified images. It figures out what the mystery input is based entirely on which group it's most similar to. It finds the closest matches and boom, it outputs a confident prediction. In this specific case, a cat.
Section 1. Meet K-nearest neighbor.
Before we dive deep into the actual mechanics, understanding a few core traits will totally demystify how KNN operates. First up, KNN is built on a supervised learning technique. And what this means in plain English is that the algorithm kind of needs a teacher. It relies heavily on a pre-existing data set of properly categorized examples to actually function. It can't just figure out what a cat is completely on its own. No, it needs a robust, available set of data where humans have already properly labeled the cases. It uses those known examples to supervise and guide its classification of any brand new data.
Second, it's classified as non-parametric. Now, this simply means the algorithm is incredibly flexible. It makes absolutely no assumptions about the underlying data distribution. It doesn't try to, force your data into a preconceived mathematical shape, like a bell curve, or make any sweeping assumptions about what the data should look like. It literally just takes the data exactly as it is.
And finally, and honestly, somewhat hilariously, KNN is famously known in computer science as a lazy learner. Why? Well, because it completely procrastinates. During the training phase, where other algorithms are in there sweating and crunching numbers to build these complex internal models, KNN does nothing. It just stores the dataset. It puts off all the heavy lifting and processing until the exact moment a new classification is actually needed. It literally waits until the absolute last second to go to work.
Moving on to Section 2, the concept of similarity.
So, if it's a lazy learner that makes absolutely no assumptions, how in the world does it actually measure the similarity of a brand new piece of data? Well, think about it like this. If we plot category A in green and category B in yellow based on their features, what happens when a new, unassigned blue data point just shows up? The algorithm judges that new point by looking at the closest neighbors surrounding it in that spatial layout. Because it physically lands closer to the green group, bam, it's assigned to category A.
All right, Section 3. Step-by-step classification process.
Let's actually play the role of the algorithm ourselves for a minute to see exactly, chronologically, how this categorization happens behind the scenes. The whole working process can be explained through these 6 very specific steps. It's actually a highly logical flow. It shifts from choosing a baseline number, which is our k, to doing some geometric math to find distances, to grabbing the closest points, counting them up, and finally making its prediction based strictly on majority rule.
Visually, our process kicks off with a new data point, let's say an orange diamond, which desperately needs to be categorized. It's just popped up on our geometric map right smack in the middle of our existing groups, the green diamonds of category A and the blue diamonds of category B. So our very first step, step 1, is to choose the number of neighbors we're going to look at. For this example, let's just say that our k is going to equal 5.
Okay, on to step 2. To find those 5 closest neighbors, the algorithm needs to calculate the Euclidean distance. Sounds totally fancy, but this is really just calculating the length of the exact, straight mathematical line between point A and point B on our x and y axes. The algorithm does this calculation to figure out the distance between our new orange point and every single training sample currently sitting on the graph.
So, the really crucial part is what happens right after that math is done. We move smoothly into steps 3, 4, and 5. After calculating all those Euclidean distances, we isolate our 5 nearest neighbors. Then, we simply count them up. 3 are from category A and 2 are from category B. Because the maximum number, the majority, is from category A, our new orange data point is definitively assigned to category A. And just like that, step 6, our model classification is ready and complete. Which brings us to section 4, choosing the magic number K.
It's a remarkably elegant process, isn't it? But you might have noticed a very specific variable early on in that little walkthrough. We actively chose to look at exactly 5 neighbors. So how do you choose the magic number K? The honest truth is there's no single perfectly prescribed mathematical way to determine the absolute best value right out of the gate. It requires trying some values to find the best fit for your specific data. However, data scientists generally find that 5 is the most preferred, most reliable value to start with. It's essentially the gold standard baseline for testing.
Now, what you absolutely want to avoid are extremely low numbers. Choosing a value like k equals 1 or k equals 2 is highly risky. Why? Well, because your model becomes incredibly noisy. If you only look at one single nearest neighbor, your entire classification could be totally tricked by a single, random outlier in the data that just happened to be plotted nearby. On the flip side, setting k to a massive number definitely protects against outliers, but it brings on some major computational difficulties.
And that leads right into section 5, strengths and weaknesses.
So is KNN always the right tool for every single machine learning job out there? Look, like any tool, it's got distinct pros and cons. On the advantages side, KNN is brilliantly simple to implement. And because it's non-parametric, it's really robust against noisy training data and highly effective for large data sets. But the real fatal flaw here is the massive computational cost. Remember step 2? The algorithm must calculate the Euclidean distance between the new data point and literally all the training samples. If you have millions of data points, that lazy learner suddenly has to do millions of mathematical calculations at the exact second you ask for a classification. That takes some serious computing power and a whole lot of time.
So, there you have it, the K-nearest neighbor algorithm, a lazy, assumption-free method that relies entirely on the power of similarity and basic geometry to make these incredibly powerful classifications. Now that you understand how it maps out the world and relies on the company data keeps, I really want to leave you with this thought. What other daily categorizations in your life, from the movies being recommended to you to the way your email automatically filters out spam, do you think are secretly being decided right now by this remarkably observant, lazy learner? Thank you so much for joining me for this explainer, and keep questioning the data around you.